Thank you, Sandeep and all organizers for inviting me. And uh, I'll briefly discuss about this topic on, AIML model has come up in the last 5 years in a big way, and it has become everybody feels that AIML model is the ultimate solution, and it is posing the hardest challenge to our numerical weather prediction community, right? And possibly there will be no NWP existence in another few years. It will be all AIML. So I will dwell more on this, but in the sense that how good is AIML model in simulating or reproducing the mean state? So mean state means, it's not 1 day variability, 2 day variability, or 1 week, or one case, okay, one extreme, one cyclone. It is not like that. It is a statistics of, say, 40 years. How does the uh, AIML model reproduce a 40-year rainfall or climatology over tropics, for example? You may ask why is it important? The next slide will show about that. Okay, this is the outline. So first I will discuss why I am, why I have chosen this heading, that mean state. So I will first show what the, this climate model. So you possibly may be knowing this. CMIP means Climate Model Intercomparison Project, okay? And we have come a long way, okay? Right from CMIP 3, so CMIP version 3, then CMIP version 4, CMIP version 5. Now the latest IPCC report is based on CMIP version 6. Now, what are these versions? They mean, they stand for? They stand for improvement. So model improves, model's resolution improves, model physics improves, okay? And it is believed that when we come from CMIP 3 to CMIP 6, so model should perform better, okay? So that I will discuss in a minute. Then I will discuss about biases in operational models, okay? Operational models is from where we get the day-to-day forecast, okay? We get forecast in a span of a day, for a week, for a month, for a season, right? And then I will just take two examples, very specific, very recent. One in the month of September, and another is in the end of August, two events. Very interesting. One in north, the other in the south, India. And the last I will come about the fidelity. Fidelity means, in NWP we use this term very frequently. Fidelity means skill, okay, skill, basically. Skill of AI model. Here I have taken specifically Graphcast, which is very popular for a reforecast for a period of 1979 to 2024. Means something like 45 years, right? So, so this is the first time. This is the first time. Okay, and reforecast means, reforecast means the past forecast. Okay, so normally in NWP we have a practice. How do we measure the skill of a model? So we start running the model from, much earlier, say 70s, 80s onward, and start forecasting and come to 2024. And then evaluate not just 1 year, 24, because it was flood or no flood, but you evaluate all the years in a statistical sense, okay, and then evaluate. That is called reforecast. Also, it is called hindcast. There are similar meaning. Okay, so please This is a recent paper, relatively recent paper. Okay, it says quantifying progress across different semi phases with the R system model validating tool. It appeared in JGR atmosphere. What is plotted here is surface temperature at 2 meter. Okay, uh, it's bias. Okay, so bias means with respect to observations. In case of model, we need gridded value, not value at just one point. We need right from south pole to north pole, okay, to minus 180 to plus 180. So this type of uh, only there is some data called reanalysis freely available. So reanalysis available from US, which is called NCEP, National Center for Environmental Prediction, NCEP NCAR reanalysis. Also, there is data available from European Center for Medium Range Weather Forecasting, which is known as ERA 5. Okay, so these are considered to be representative of observations at every grid. Okay, so one can actually, yes. Pardon? NCEP and ERA 5. So see, there are. So let me tell you, there are four very popular reanalysis in the whole globe, which the numerical modelers use for validating their model. One is this NCEP-NCAR, very widely popular. They have data right from 1949 onwards. Then we have this ERA 5 developed by ECMWF. We also have a Japan Met Agency reanalysis. It is called JERA. They also have a 55-year reanalysis. We also have a NASA reanalysis called MERA. Now, there are papers actually, okay? If you take difference of any field, okay, temperature, geopotential, they differ, okay? Yeah, they differ. So, ideally speaking, our ground truth is the observations in situ, okay? But unfortunately, we don't have these in situ observations at every grid point across the whole globe. So we have to depend on some reanalysis. And because ECMWF, we believe that ECMWF model is highly accurate, okay? And the data they assimilate also is maximum among all. So we have a reason to believe that ERA 5 will produce the most representative state of atmosphere. So now if you subtract, okay, this is not projection, okay, this is the historical natural, okay, so kind of present. Now what you see here, uh, this is CMIP 3, okay, where my uh, pointer is, okay. This is CMIP 5, this is CMIP 6, and this is actually, there is a group of model which is now considered to be high resolution model. Okay, so they have, I mean, clustered all the high resolution model. So they called it high-res MIP. And there is a relatively low resolution model. This is low resolution MIP and so on. But now if you see, without going into the details, okay, you ask any layman, he or she, they will very clearly say, aha, your southern hemisphere is always warmer and northern hemisphere shows to be cooler. And this signal persisted right from CMIP 3 to CMIP 6, right? And you may argue, no, see the color, this blue color has slightly faded, so the bias has improved. Answer is yes. But again, if you come to high-res MIP, you can see the blue color has increased. So you may argue, so in high resolution, error has increased. That also answer is yes. Then I will show you to some specific spots. For example, here to the west of South Africa, over Chile, Peru coast, over California coast, and so on. These are the area where we have, cold SST. Okay, that's why we have low clouds throughout the year. And climate model has systematic bias in resolving low clouds. Okay, because low clouds normally cools, right? Low clouds cool the surface. It is not resolving the low clouds, so it is warming the surface. So right from CMIP 3 to CMIP 6, you will see wherever there are low clouds, including southern hemisphere, you see the temperature is warmer, right? So this bias also persisted. This bias is directly linked to uh, ability of the model to simulate low-level clouds. Okay, so this is one. This is about. Pardon? No, it's not forecast. This is a free run for, like it is mentioned here. CME 5 is 85 to 2004. CME 6 95 to 2004. Okay, for the whole time. This is a mean. So we keep in mind, say, I was giving an example. So if I take my weight in the morning, then afternoon, then evening, and go to the doctor and tell, morning I was a little lighter, afternoon I am becoming heavier, the evening I am becoming lighter. Is it a problem? You will tell what was your average weight in the last 1 month. Is it systematically decreasing or increasing? Then only come to me. So it is like that. Last, say, 20, 30 years of mean, it is robust, it is statistically significant. Yes. So it is like, it is current. Okay. So model average, current. So because we feel that, climate change doesn't happen in just 30 years, it happened beyond that. Okay. So what is the take home message? The take home message is that the models, in spite of some improvement, the systematic error is persisting. Okay, whether I'm increasing the resolution, decreasing the resolution. Okay, CMIP 3, CMIP 5, CMIP 6. This is for temperature. This is more serious. Okay, so this is rainfall. Okay, and green means more rainfall, more than average, and brown means lesser than average. Okay, negative and positive. What you see again, without going into the detail of nitty-gritty of the figure, you can see the whole global tropical ocean, right? Tropics, ocean also, so you can just check yourself. The whole global tropical ocean is showing green patches. So it is raining more. And the global land masses, or even extratropical land masses, they're raining less. So there is a weight bias in terms of NWP. Technically, we call it, the model has weight bias over ocean and dry bias over land. So it means that, see, in this case, we don't use ERA 5. For rainfall, we have different data set, like Global Precipitation Climatology Project, GPCP. It is very widely used. 1 degree by 1 degree rainfall data. That data is used here. And so what it shows is that model is raining more over ocean, less over land. Okay. So it is very, evident that, if it rains more over ocean, so moisture is getting exhausted over ocean, remaining only is coming over land. So whenever you ask this model to produce extreme, it will naturally find it difficult. And moreover, if you see the biases right from CMIP 3 to CMIP 5 to CMIP 6 remain kind of same, even in high res and low res. Okay. Again, you can argue, no, some dark green has become slightly lighter green, okay, here and there. Some dark brown has become slightly lighter brown, and so on and so forth. But still, broadly, we could not resolve this bias. And this is connected with the, the simulation ability of the model to simulate clouds, as you can see, this is basically the shortwave cloud radiative forcing, okay? And you can see here there is a huge deficiency over global tropical ocean, which has of course improved, okay? And there is error over land as well. So eventually, we can conclude that the climate model, these are all climate models, okay? These are all coupled climate models. So there is ocean and atmosphere coupled, okay? They have some kind of a bottleneck due to which they are not able to overcome the systematic bias, which is persisting for last maybe, 20, 30 years. Now, this is a version of a model which is currently in use in India, okay? India Meteorological Department, they use this model. This is developed by US, National Center for Environmental Prediction, NCEP. And two resolution, this is 126 triangular truncation, means around 100 kilometer. This is T382, means around 38 kilometer. Okay, so high resolution. But again, if you see, uh, there are huge rain over ocean and less rain over land. Okay, and also you see there is a clear kind of two ITCZ structure evolved in the model, okay, which is again unrealistic. Now this is about, this is what we call a diurnal, sorry, not diurnal, this is just to give you an idea how the cloud and rainfall are associated, okay. If you see here, so this is observations, okay. I plot the trim precipitation rate millimeter per day in the x-axis and Velar outgoing long wave radiation in the y-axis, okay. And when Velar value is less, it means I have deeper cloud, okay, because deep cloud stop is at the very high, so it will have lower temperatures, so produce low outgoing long wave radiations, okay. What you see here is that, we have, when the rain rates are higher, 30 millimeter per day, 40, etc. See, the Velar is going down lesser than 180, this line, right? And when I have a lesser rain rate, then the Velar is high. So it means that lighter rain rate are coming from shallower clouds, heavier rain rate coming from deeper cloud. It is, common sense also says that, right? But when we compare that with our model, you see what's happening. Irrespective of the resolution, as I showed in the earlier figure, you see you will find hardly any dots coming below this 180 straight line, right? So it means that the model is only producing very, lighter rain rate from the shallower cloud continuously, okay? And that's what is one of the reason that we get, lot of rain over ocean, where you get a lot of lighter cloud and drizzle rain rate. This is another example where again from the same model, CFS. This is the observations. You see, this is actually diurnal. Okay, within a day. Okay, it is early morning, very early morning, then middle of the day, then in the late evening. This is the probability distribution, and you see that see when you this red color, brown color, etc. These colors, so heavier rain rates are coming when you are going towards evening or late evening. Okay, and when you are in the early morning, you get mostly the lighter rain rate. So this is the variations within a day. What the model is producing is like a hockey stick. So it means that throughout the day, it only produces very light rain, okay, and then the heavier rain rates are very less. This point you keep in mind, because when we discuss the AI model, this point will come back. Okay, this is another aspect. Okay, in the tropics, in the geophysical fluid, we also have some waves that carries energy. Okay, we call it convectively coupled equatorial waves. Okay, one of them is Kelvin wave, another is that equatorial Rossby wave, and another is mixed Rossby gravity wave, and so on. These waves are important because many of the tropical disturbances are, they get triggered by these propagating waves, okay? Now, what you see here, this is the observations, okay? So you can see a very strong presence of Kelvin wave, but the moment I come to CFS, okay, I could hardly see that power, okay? So the Kelvin wave is very weak. The mixed Rossby gravity wave also is a fast-moving wave in the equator, which is very much prominent, which again, we could hardly see its presence, whereas equatorial Rossby wave is, kind of overestimated. So the point is not only the precipitation, its variability. Okay, so I showed the precipitation, which is mean, right? And what we get day to day is the rainfall variability, which is caused actually by these tropical waves. So they are also kind of not realistic in the model. Another, metric that we use is that, this is what is called ISO, intraseasonal oscillation, which is normally, we call it a 10 to 90 day oscillations, okay, 10 to 90 day kind of MJO, low frequency oscillation. And there is a high frequency oscillation 2 to 10 day, okay. Both these frequencies are embedded in our rainfall time series. And what you can see is, this is the observations. You can see here that ISO variance is rather less, okay. Whereas in model, you see the ISO variance is much, much high, okay. And exactly opposite is our, synoptic variance. So synoptic variance is much less in the model and much high in the atmosphere. So again, it shows the same thing. The convectively coupled equatorial waves are weak, and synoptic variance, means synoptic activity, are weak. Models are running more in ocean and less in land. So they are all consistent. They are only indicating one thing unanimously, that you are going to get less rain from this model over land and more rain over ocean. Now, coming to extremes. Okay, so all the mathematics students and otherwise also, you all know this is a what I am trying to say is 1 sigma, say a distribution, and here in the tail we define it as 2 sigma. If I go further, I get 3 sigma, okay, and so on. Now, what is actually happening now, okay, this is a table from, Kerala rainfall of 1 to 19th August 2018. If you see in these 19-20 days, actually, the rainfall that happened was 164%, okay? This is something unusual. The next table is more, disturbing. We have calculated both the, 20, some 2 weeks rain of 2018, 2 weeks rain of 2019. Both these weeks produce havoc. And if you see, we have a paper actually, weather forecasting. If you see, this is the standard deviations, okay? So just now you saw the 2 sigma, 3 sigma, we reach almost in the tail of the distributions. Here, what actually has happened is 40 sigma, okay? 74 sigma. I mean, this is kind of crazy, okay? 64 sigma, Waynard, okay? This is 18. The same thing almost repeated in 2019, okay? 44 sigma, 59, 72. I mean, this was a tremendous, kind of 1 in 100-year phenomena. And and this is the, I mean, which district got how much, okay? This is the rainfall distribution 2018, and this is 2019. Now question is, how do the operational model perform for this event? Look at this. So this is our IMD GFS running at 12-kilometer resolution, okay? And all these black lines are actual IMD observations, okay? Averaged over that region, okay? This red line everywhere, it is the climatology. Climatology means what? Long-term mean. Okay. So it means on 6th August, Kerala is expected to get this rainfall, which is signified by red bar. Okay. So, it is not changing much. So climatological mean is very low. What actually has happened, you have seen the table previous slide, it is multiple times than the climatological mean. Okay. Now you see what the model has done. This is deterministic, one version of the model. Okay. You can see this green bar is the 24-hour day one forecast. Okay. This forecast only is trying to somehow catch up with the black line. But all other days, okay, when you are going to second day, third day, fourth day, fifth day, this is sharply decreasing. So it means it is not capturing the rainfall, right? This is ECMWF, okay, from European Center. You see the story is not different either, right? It's changing. And this is a unified model from UK. It is being run here in Noida by NCMRWF. So that's why it is called NCMRWF Unified Model. The story is somewhere it is slightly better, but things are not in place. Okay, so beyond day one. So the take-home message from this is that the models are not able to capture this extraordinary, exceptionally heavy rainfall more than 24 hours. Okay, somehow in 24 hours. But then question is 24 hours. If you ask any IMD person, is 24 hours sufficient for giving warning for such a heavy rain? Answer will be no. Okay, so then let us redefine our question. So in spite of all these biases, in spite of all these model limitations, the demand at the society is that you have to predict this type of rain uh, with accuracy of magnitude and with a longer lead time. Means you have to give the prediction 4 or 5 days or 3 days in advance so that people get sufficient time, administrator gets sufficient time to evacuate or safeguard the lives and properties, right? It's not happening. Now, what was the weekly forecast? This is by ECMWF during that time. Okay. See, 13th August to 19th August. So this is analysis. You can see here, very heavy rain, but ECMWF completely missed the event. Okay. Their weekly forecast completely missed 2018 Kerala flood event. Okay. That's what this figure is showing. I got this figure from our friend Roberto Buiza. What was the weekly forecast or subseasonal forecast from other centers? Like this is from NCEP, CFS. You see, this is actual rainfall, and you can hardly see the rainfall in. So some rainfall was there over ocean, not over land. Week 1, week 2, from week 3 and week 4. Actually, it shows no rain. Okay, negative rainfall anomaly. And this is from that time NCMWF 60 kilometer. So you can see here also in week 1 you get something, but then week 2, week 3, week 4, you don't get any indications. Okay. So this was the situation in 2018, 2019 flood. And as a result of that, what has happened. But then, we started thinking, and there was a paper by Peter Webster about Pakistan flood. And he said, no, the ensemble prediction can provide you some guidance. Okay. So in this paper, actually, we have argued that yes, ensemble forecast provides some, effective probability of heavier rain, at least 4 to 5 days in advance. Here one small example. So there was an event in 31st December 2021 over Chennai. Okay, Chennai normally gets rainfall during winter because we have northeast monsoon setting in. Okay, so you can see here, this was from the observations. You can see, and that event one day, okay, it was 140 millimeter compared to the Chennai climatology. It was, so it was beyond 10 standard deviations. So 10, 12, 15 standard deviations. Okay, and naturally, this deterministic model did not produce much information, whereas the probabilistic model, it still, produce some 70 to 80% of, probability for up to 3 standard deviations. We cannot go to, you have seen the tail, okay? Model cannot produce, we don't have any model currently, which can produce any figure of 10 standard deviation. Forget it, it cannot. So what we decided is forget 10. If the model can produce 3 standard deviation, that itself is a great thing, okay? So we considered 3 standard deviation. So some, there is a shift, but still it is capturing something, okay? Yes. Hmm. Yes, because see, the advantage is, so it's a good question. So, so advantage of extratropical countries or mid-latitude countries is that there all the, weather disturbance, they are not influenced by this convectively coupled equatorial waves or all these complex interactions of, okay, ocean, atmosphere, etc. They are mostly embedded system in the westerly regime. Okay, so wind will come. That's why the Wimbledon forecast is so accurate, and many other places. So always it will come from west to east, and the troughs are embedded in that. So weathers are fairly accurately predicted over across the globe in extratropics. Okay, but the moment you enter into plus minus 30-degree north to south, the model loses skill, including ECMWF. Yeah. It is now due to satellite data gaps have been full, uh, this thing. Yeah, but if you calculate, theoretical predictability, okay, taking the nonlinearity of the system into account, taking the chaotic behavior of the system into account, taking the butterfly effect into account, you will see that, I mean, what we have seen in our paper, that the error grows so fast. So if we do a, identical twin experiment in a fair weather and in a convective atmosphere, okay, we find that the error grows very fast in convective weather. Okay, so 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 by the time my error crosses my mean, it loses all the predictability. So we cannot really go so far. I mean, so the point is, if we concentrate on low frequency oscillations, slowly varying, this thing like intraseasonal oscillations with the 30-60 day periodicity, we still get some predictability from ocean, okay, and El Nino and so, or IOD and so on. So it adds some, we get some source of predictability. But for extremes of this kind, we don't get, we are clueless. There is no atmospheric parameter that gives you guidance that can help you to predict this, okay? Yeah, it is not. Yeah, that's a different maybe discussion. Possible, yeah. But question is that no. So question is it is really so pessimistic? I mean, there is no hope. So let us come to that. I think there is some hope. So now there was a paper by Dr. Rajivan, and this Saikranti is from IISER Tirupati. Yeah. So this paper is this is the first paper. This is the first paper written on the trend of subdaily scale. So far it is only discussed about whether it is Goswami 2006, even Rajivan 2010, Roxy et al. And so on. They have all analyzed daily rainfall, daily 24-hour rainfall. This is the first paper where they have analyzed sub-daily scale rainfall. And sub-daily means, within a day, okay? And this sub-daily scale rainfall is not available. If you Google it, you will not get this data anywhere. So they have actually generated the data. They have gone into the logbook and collected the data, okay? And it's a huge work they have done. But see, self-recording rain gauge hourly rainfall data from 1969 to 2010. Okay, it's a gigantic work they have done. Okay, and these data have been utilized to identify the rain events. Okay, so they have actually collected the in situ rain gauge data and this uh, subdaily scale. The conclusion is that in India, frequency of short duration heavy rainfall events are increasing. That they have found out. So short duration heavy rainfall events. What does it mean? It means this. Because I am located in Berhampur, so I got to know about this event 2 years back. One of my IMD friend, he shared with me. So Bhubaneswar suddenly got flooded. Okay, in 31st August. What went wrong? So this is UTC, okay? So you have to add 5 plus 5:30 to get Indian time. So you see, morning was perfectly fine, even noon was perfectly fine. But then in the late afternoon, the rain started from 0.6 centimeter, so something like 18 centimeter, okay? So something like, so kind of cloud burst, but we don't know. Cloud burst has to be 10 centimeter per hour, but it is in 3 hours, almost 20 centimeter. So huge rainfall. So this is short duration, extremely heavy rainfall. This is increasing, okay? And the fact of the matter is we don't have any guidance as of today. If there is 20 centimeter rain in 3 hours here, this also will get flooded. This is from rain gauge. You have automatic rain gauge. Yes, you have automatic rain gauges. So it is not there in every places, but where they have some, they call it class 1 observatory, okay, like at least where there is an airport. So they have this, continuously measuring rainfall measurement. So yeah, and what they have done is self-recording rain gauge. So they have collected this data, self-recording rain gauge. Okay. Okay. So this is, so we understood the problem in the observations. We understood the problem of model. Now 2025, we all aware that look at this September 2025, 1st September to 3 September. Okay. The rainfall country as a whole, country was raining, so it was 84 percentage. But Northwest India, okay, it was 300%. Okay, this is unthinkable. Okay, actually, this is the cause of Punjab flood. Okay, so now you have seen 164% what caused Kerala in 2 weeks. Now it is 300% in 3 days. Okay, and somewhat in the whole state. Okay, so this is unthinkable. And now where we are, so this is there is definite improvement. Okay, so this is the extended range forecast, weekly forecast from IMD, and you see from 28 August to 4 September, this week, which actually includes 1st to 3rd September, you see this Northwest India, it is definitely showing more than normal, rainfall. But this does not indicate that whether it will be 300% or 200% or 10% or 5%. That information you don't get here, okay? And then you have 4 September to 11 September, but you see here, the uncertainty you see. The next week, the same forecast, same system, when it predicts this next week, you see this 4 to 11 September rainfall was here, okay? It is a week 2 rainfall. Now here week 1 scenario has completely changed, okay? Now you see a big blob here, okay? And there is completely dryness here. There was even rainfall over Odisha and this area, Jharkhand and so on, all have gone. So now question is, if you really, if you believe on this forecast system, and you feel that the Gujarat and other area will be perfectly okay, you will be wrong, because the next revision, okay, suggests there will be a huge rainfall. But at the same time, during 4 to 11 September, this area did not produce 300% rainfall, which was actually realized this. So this is the kind of uncertainty embedded in the forecast, okay, which the disaster manager and forecaster they are handling and dealing with. Now, how about the weather scale model, which IITM is producing and IMD is using? So this is the rainfall for 31st August initial condition, 1st September, means it is just 24-hour forecast. Okay, you can see some patches, okay, which are mostly fall between 4 to 8 centimeter, which is not considered to be very heavy. It is just heavy. Okay. When you go to again, 1st September initial condition, forecast for 2nd September, you get slightly heavier here, okay, but still not beyond 8 centimeter. And on 3rd September, actually, the rainfall patch moves away. Yeah. No, this is not. I'll come to ensemble. This is deterministic. Okay. Now, below is the ensemble. You see GEFS. This is the ensemble probability. I have only kept the probability of heavier rain, 65.5, 115, and 195. These are the three categories which IMD considers: heavy, very heavy, and extremely heavy. Okay. Now you see here, you don't see, and below is the level of probability. If there is blue color, it will mean that there is a 25% probability of this rain to happen. Okay. If there is green color, then there is 50% probability of this particular rain to happen, and so on. Now you see all map is blank. Okay. So question is, so now this is going actually, and here, okay, here you have the deterministic forecast for extremely heavy, okay, 6.5 centimeter and above. So question is, neither your deterministic forecast nor your ensemble forecast is able to capture this heavy, not that heavy, not forget 10 sigma, not even 1 sigma, okay. And as we have shown the biases, it is still producing lighter rainfall and trying to struggle with extreme. This is the fact. Now, why it is happening? Recently, one PhD, one of my who is doing under me. So this is from deterministic, okay, model reforecast. This is IMD 0.25 degree data. Okay. If you plot the 99th percentile rainfall, okay, for June, July, August, September over whole India, but you can argue that IMD rain gauge data that was used to generate 0.25 or 1 degree, there are some caveats because the number of gauges were not uniform, etc., etc. So let us consider the central India, where it was pretty uniform. Okay. So what do you see here? See, there are green and yellow color, right? So it means something like 80 to 100, right? 220, this range rainfall is coming up as a 99 percentile rainfall in climatological sense from the IMD's observed data, correct? Okay. Now where my model stands, forget ensemble, just take the deterministic. One model, 24-hour forecast, just 1 day forecast, you were still able to see some blue and green patches at the central India, right? But then from day 2 and day 3, all have gone. What does it mean? It means that, see, this blue color means it is just 4 centimeter, 4 to 6 centimeter. It means that your model climatology is so erroneous, okay? It is now capturing 4 centimeter rain as a 99 percentile rain. You can't do anything. Because if you take the model rainfall series, you see your maximum rainfall is 4 centimeter, that's all. But that doesn't make any sense. That is of no use, basically. And because of that, when you are trying to extract this information, what is the probability of 11.5 centimeter, which is considered to be extremely heavy, very heavy rain, or 20 centimeter, which is extremely heavy rain? Model is clueless. Model has no answer. Okay, so keep this in mind again. So this is the forecast. This is the reason. Then we thought, okay, one of the possibility is that resolution. Okay, so Siddharth is sitting here, and others are in IITM. So after a lot of struggle, almost 4 years, 5 years, this model was developed. We called it IITM High Resolution Global Forecast Model. This paper published this year, and it has some speciality. What currently is used, GFS, it is called Gaussian linear model. Okay, means right from the South Pole to North Pole, you see it is broadly 12 kilometer, 12 kilometer. Okay, so it is running 12 kilometer Arctic also, it is running 12 kilometer Antarctic also, even though we are not using that forecast at all. Okay, so computer is getting utilized. When we come to this particular grid, which is known as cubic octahedral, the details are there in that paper. Then you get like a butterfly, okay, where gradually the resolution increases towards tropics and then increases over extratropics. It gives you some leverage in computation. Okay, if you zoom it, you can actually see that over equator, it comes almost to 6.5 kilometer across the global tropics. So now, where does this Punjab stand in this model? Okay. Now this is the observations. Okay, I have kept the observations here. Now you see, this is the 31st August initial condition, 1st September. Here, this is 1st September initial condition. Second, this is second initial condition. Third. So you can see here the colors are slightly deeper, darker. Okay, you can tell I am biased. Okay, you can tell that when you were discussing the climate model, then you were telling colors are not so important. Here you are telling colors are important. That is a human biasness, but it's not significantly different. Okay, but slightly. I mean, if someone can take a difference between this model and that, you can see some positive this thing. But you see, I will draw your attention to here, in the Bay of Bengal. You see, there is a significant underestimation. Okay, Bay of Bengal is the breeding ground of all our weather system. Okay, and that is influenced by SST, that is influenced by convectively coupled equatorial waves and many other factors. And even this 6 kilometer is not doing a great justice to this bias. Okay, coming to IFS, got this plot from my friend Peter Bechord. Now he is retired, working as a consultant. Now you can see very clearly that it is producing a lot more rainfall. Okay, we just can't. I mean, ECMWF is ECMWF. Okay, it is 9 kilometer though. Okay, even coarser than 6 kilometer, but still it is producing. See here, something like 84 millimeter, millimeter, centimeter, whatever. So it is very, it is producing a lot of rain there. And yes. Yeah. NCMWF. No, 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 no. No, no, no. See, ECMWF initial condition we can't get. You have to purchase. Okay. So we have adopted the ECMWF grid in our model. Rest of the thing, everything, that's why its name is Bharat Forecast System. So Question is, it is giving better forecast compared to what we have earlier. It is giving, yeah, you know. So Indian, whatever we have 12, so it is producing better than 12. But the proof is in front of you. It is definitely not closer to IFS. You can see it here. And you can, so you check it. See the Bay of Bengal rainfall which it is capturing, okay? Okay. But then, you know, everything is not so bad. We have this 12-kilometer ensemble forecast. From there, we use the climatology of GFS, all ensemble, and then compute what is called extreme forecast index, okay? EFI, that ECMWF also does that. And EFI was exceptionally good, you see, even with, you know, in all those days, okay? So what we, I mean, if you hear any of the talks by Tim Palmer, he always hate analyzing deterministic model. He will always argue that because of chaotic nature, you always analyze the probabilistic part. And this is the metric which is called extreme forecast index. Because we are running 6-kilometer model as a one single member, so we cannot generate EFI, okay? But 12-kilometer model, you see, it is generating very strong red color, means is seriously something very extreme going to happen. But this index does not tell you how much rainfall it will happen, okay? But it genuinely tells that, you know, extreme rainfall is going to happen, okay? And if you get this, this EFI consistently over same region for next 1 or 2 days, then you can be pretty sure, because it is 21 model, not one model. 21 model is suggesting, based on their own climatology, that there is going to be extreme. So you should avoid by that, okay? So this is a good thing. This is a hopeful thing. Even though deterministic model is not working, that probabilistic thing is giving you a correct signal. But then the other event, I think hardly any people noticed it. I am in Berhampur, so I was reading the newspaper and I got this, okay? During 27th to 29th of August, okay, there was a district in Telangana called Ramareddy, okay? This district got 40% of its annual rainfall in 3 days, okay? And everything got, you know, devastated. So there is a long story, but if you see the communication gap, this is interesting. They say that while the IMD insists a red alert had been in place for 24 hours, right? State officials dismiss it as a routine alert or too vague to trigger adequate preparedness. So this is the problem. So this is a problem, okay? So you are, so the red alertness, okay, is not working. They feel that red alertness is too routine. Maybe many other days red alertness has been given and things have not worked. So, and when I was looking at the, again, I'm not showing the deterministic forecast, but I looked at, you know, again, EFI from GEFS, okay, it actually gives a clear, you know, very high value of EFI. So this is very pleasing to me, that probabilistic system is working well. And this here, there is, you know, there is a, what is called is probability of 90th percentile and probability of 95th percentile. You know, 90th and 95th percentile is considered to be extreme, okay? And it shows more than 75% chance of a 95th percentile event to happen over that area. So if you get these two, okay, informations in your hand, you can definitely do some, what is this? Okay. But anyway, if you look at the, can we remove this? Okay. If you look at the ECMWF forecast, okay, on 24-hour, it actually gave, you know, some forecast over near Telangana, but they also fail on 48 hours, okay? So their deterministic system also doesn't work every time, okay? This is the uncertainty. Okay, now I'm coming to the final portion, which is the AI part. Okay. Now see, this I have plotted. IMERGE, possibly everybody knows. This is the NASA generated rainfall, right? And this is the climatology of 20 years. Okay. And this is the climatology over, you know, Indian and surrounding region. This is the standard deviation, which basically, square it to got it variance, represents the variability, right? So you get, lot of variability over Whirlpool region, over hit Bay of Bengal region, mind it here, okay, here. And you see there is a good rainfall over hit Bay and all these regions, okay. Now, see, this is the first time, okay. Nobody has plotted the AIML climatology, okay. This is from 1979 to 2024. So I'm really extremely pleased to see that, it has really captured exceptionally well the global precipitation climatology, okay. You see there is a tropical maxima here, see the Bay of Bengal maxima here, see the Western Ghat rain here, see the South Equatorial Convergence Zone, and there is also a Western Pacific Convergence Zone. There is no double ITCZ. There is, I mean, this is something unparalleled. I can bet any climate model reproduce this. Okay, this is not coupled, by the way. So this is very, very encouraging result, I must say. Okay, very encouraging. Look at the GFS. This is one of our colleague in IITM just communicated. So why I plotted GFS? Because GFS also is an uncoupled model, like Graphcast, right? But you see, when you go from day 1, day 2, by the time you come to day 3, it starts producing a double ITCZ, gets disconnected, right? And this is, I'm just going to show you. What do you show? Oh, okay. I'm finishing. Yeah. This is, this is a paper in GMD, recently published. You must have heard about a hackathon, an experiment going on globally. Okay. So here they have compared two very state-of-the-art model, ICON coupled to land, ocean and ice, and also IFS. This is finite volume sea ice coupled model of IFS. But this is non-hydrostatic and this is hydrostatic. Both are running almost at 5 kilometers. They have run it almost for 30 years to generate the climatology, okay? Both these models are actually participating in hackathon, okay? But now if you see, this is the result, okay? ICON produce a clear, double ITCZ, okay? And IFS, even though hydrostatic, it produces a much better climatology, okay? Now you can just think about what I just now show from Graphcast, right? And if you see with latitude, the rainfall, so ICON is nowhere around. I just asked my friend Peter, what went wrong in ICON? It looks so horrible. He said they switched off the shallow convection. I don't know, it is his comment. But anyway, ICON is not realistic, okay? And this is the, JJ's mean for, again, Graphcast. This is fantastic, okay? This is just amazing. This is a variability, okay? You see that model, although the color is different, things are prepared hurriedly. So you see the Whirlpool region and the Head Bay of Bengal over West Coast, it shows a lot of variability, okay? Which most of the model fails, okay? But then all is not quite on the Western front, okay? This is the, bar diagram. It's very important. Remember what I showed earlier. This is from trim GPM, IMERGE, okay? What you see is that this is a percentage contribution of rainfall to the total rainfall. So you find that 10 to 20, 20, 30, 30, 40, 40, 50. This range is contributing maximum in your total rainfall, okay? This observation is saying. Graphcast, no, this is the problem. So it shows that by the time you come to 30, 40, okay, its contribution has gone. Okay, so it is majorly contributing in the lighter rainfall. So model is again producing lighter rainfall. Lighter rainfall is contributing more to the total rainfall. Okay, which is not quite correct. Okay, I plotted the CFS model results also. You see the lighter rainfall. So here it is not going as per the last 2-3 slides. This is a northward propagation for 20 to 24 from IMERS data. You see, it is natural that northward propagation will start from 10 south, go to 30 north. Again, there will be break, again active, then break, active, and so on and so forth. It continues, okay, on an average 3 pulses per season or 4 pulses per season. But then when we apply the same thing to Graphcast, no, it doesn't look realistic at all. Okay, it is showing too many, okay, too many northward propagations. So the question is that we have to, sit and think where the mean state is going wrong. Okay, whether we are getting correct result due to wrong reason. Okay, and anyway, and this is just, we plotted this that, even Kerala rainfall from ForecastNet and Graphcast, you can see the model is not capturing these, hotspots of Kerala rainfall. Okay. Okay. Recently, there was a paper from Weather and Forecasting where they have initialized Graphcast from GFS and IFS. Okay, and compared this both the model. If you see here very clearly, so this is the skill score, equitable threat score. They have gone up to 168 hours, means almost like 7 days. Okay. If you see, the point of concern is when you are going to higher rainfall rate, okay, the Graphcast model, both are falling below the GFS and IFS. Okay, that's the point of concern. Because it is producing more lighter rain, as you have seen. The last slide. So what we are proposing is that, neither NWP alone can break this bottleneck, nor AI alone can break the bottleneck. These slides I am showing for last 2-3 years. Hopefully, we'll be able to do something. So there is another word called super parameterization. I don't want to go into that into detail. If you have the super parameterizations, you can actually extract the tendencies of temperature and moisture from that and build a deep layer, okay? And you can train actually, basically. And this trained, temperature and moisture can be given to each GCM grid, okay, as a for convection. That's what I have written here. Use SP GCM CRM tendencies for a year to train and build the deep layer. Use the output of trained tendencies in the GCM, and then test the NN GCM forecast in forecast mode. Look at this. This is a animation from Pierre Gentin and Stephen Rasp and all these people. So this is a super parameterized CAM model, and this is the, what is called neural network, artificial intelligence model. Okay, and this is the difference. If you see a little carefully, okay, you see this SP CAM, it is producing a lot of flashes, right? Whereas this is to somewhat quiet, right? Yes or no? The AI model is somewhat quiet, and this is producing a lot of flashes. It means it has more variability. It has less variability. Okay? It has much more smooth. It's much more turbulent. Okay? And that is similar here as well, and you can see it here. So anyway, I stop here. And any questions? Thank you.
I have one question about the Graphcast, hindcast.
Uh-huh.
So, as far as I know, Graphcast is kind of trained from 1979 to
Okay.
around 2015.
No, I think this is a separate data set they have used.
Okay. Yeah.
For recent.
So it's not the Era 5 reanalysis.
Yes.
Okay.
Yeah. So yeah. Any other? All problems solved. No need of MOU tomorrow. I'm kidding. Any of it? So, thank you. Oh, you have a question, Professor Rao. Sorry. Yeah, please.
I know you're showing Graphcast, but some of the other ones seem to be also doing quite well, especially the one,
Some of the other models.
yeah, AI models,
Okay.
including the new one from Microsoft.
Yeah.
So there are studies indicating that they're getting the physics, especially things, complicated things like, your monsoon depressions.
Mm-hmm.
So, um, is there any way to look at these not just in a statistical sense,
Yeah.
as you've done,
Yes.
but in a dynamical sense to understand whether physically they're getting what they're supposed to get right?
Yeah, it's actually we are. Let me tell you two answers. One first answer is that apart from Graphcast, no other AI model has come up with any reforecast of such a long time. They are all running in a very piecemeal way for one season, for 1 year, things like that. They have not run for 45 years, trained it, and produced this hindcast data. It's not available. So we actually don't know their real skill in statistical sense. Number one. Number two is it is true. Actually, I had a discussion with the Tim Palmer. He also says that you generate the you know butterfly from the AI models. Okay, can you generate that? He said, my gut feeling is you can't. Okay, so one metric. So we will try some dynamical test as well. Okay, this is a very first attempt. We are going to write this as a paper. Many more analysis will come, and of course, we will include dynamical as well. Any other questions? Right. But people who are online will not hear you.
So you said that no other AI model has gone for that long.
Yes.
So what do you mean by Graphcast? Because the lead time isn't 45 years, right? So what do you
No,
mean
no,
by
there is no lead time here. This is just climatology. This is climatology. Where is it? This is climatology. We are not, like this is the climate. Okay. So we are not evaluating day one forecast, day two. No. Okay. Done? Good. So PPT is here. You can take it. Anybody who wants.